Imagine standing right in front of a massive industrial building. Honestly, from the outside, it looks surprisingly, well, almost disappointingly ordinary. You're just looking at gray walls, some standard loading docks, and security checkpoints with employees swiping badges through controlled gates. There are absolutely no flashing lights, no dramatic neon signs announcing that history is literally being made inside. But, as you'll see in this explainer, appearances can be incredibly deceiving.
Because while the outside is just boring, unremarkable concrete, the second you step inside, you are entering the world's most advanced factory. Inside those walls, machines are performing some of the most precise manufacturing humanity has ever attempted. We are talking about building products measured in billionths of a meter. It's a level of precision that's almost unimaginable. So let's really dive into this, because I promise you, this isn't your standard car factory or airplane assembly line.
What we're looking at is a factory that manufactures the tiny computer chips powering, well, pretty much everything. Every single modern economy relies heavily on what happens in these specific rooms. Smartphones, those massive new AI models, satellites orbiting the Earth, electric vehicles, cloud data centers. Without these microscopic pieces of silicon, our entire modern civilization would just grind to a halt. Figuring out how to make them at scale has become one of the absolute greatest engineering challenges we've ever solved.
All right, moving into Section 1, From Sand to Silicon. And as the subtitle says, the journey begins with ordinary sand.
It's kind of wild, right? The foundation of our most advanced technology starts with one of the most basic, everyday materials on Earth. But trust me, it doesn't stay ordinary for very long. Through an incredibly controlled chemical transformation, we do three main things. First up, we purify. The silicon has to be refined to extraordinary levels. Any unseen contamination, stuff far, far too small for the human eye to even see, can completely ruin the final product. Next, we crystallize. That perfectly purified silicon is carefully grown into these massive cylindrical crystal structures. And finally, we slice. Those giant crystals are cut down into perfectly smooth layers known as wafers.
To put that into perspective, consider the sheer physical scale here. Each of these perfectly smooth silicon wafers is actually thinner than a few sheets of paper. Yet eventually, that delicate, ultra-thin disk is going to hold hundreds or even thousands of highly advanced processors. The amount of sheer computational power they pack into such a fragile, paper-thin space is just staggering.
So that brings us to Section 2, Carving Circuits with Light, the magic of photolithography. Okay, so getting a perfectly smooth wafer is a huge achievement. But really, that's just setting up the blank canvas. Now comes the real engineering magic. To carve billions of microscopic transistors onto each wafer, standard blades or even lasers just won't cut it. Engineers have to use photolithography. It's the process of projecting intricate patterns with light onto light-sensitive materials, carving microscopic circuits layer by layer. So basically, these specialized machines project patterns, and the circuits gradually emerge on the silicon. And get this, each new layer has to perfectly align with the previous ones. You are aligning thousands of intricate patterns while working at a scale that is literally smaller than many viruses. If you're off by just a few nanometers, the entire chip is totally useless. Because this level of precision is so extreme, the machines that actually do this are among the most sophisticated tools humans have ever built. To give you an idea of how crazy complex they are, transporting just one single lithography machine requires multiple huge cargo aircraft. One machine. They take years to assemble, contain hundreds of thousands of components, and represent decades of intense global scientific research.
And the craziest part? Over 1,000. Lithography is literally just one step in the process. A modern semiconductor passes through more than 1,000 different manufacturing stages in a continuous 24/7 cycle before it's actually finished. The wafer is repeatedly coated, exposed, etched, cleaned, heated, polished, inspected, the whole shebang. Every single second matters in this cycle. Shutting down production for even a brief moment is extraordinarily expensive.
Which leads right into Section 3, the billion-dollar clean room, keeping the modern world spotless. So to successfully run a 1,000-step process at a microscopic scale, the environment around it has to be absolutely flawless. We're talking about clean rooms that are thousands of times cleaner than a hospital operating theater. You know what the biggest enemies of a computer chip are? They're completely mundane things. Human hair, everyday dust, skin particles, tiny little specks floating harmlessly through the air in your living room right now could instantly destroy these advanced semiconductors. It's actually incredibly ironic. Engineers have to wear those intense, full-body protective suits not to protect themselves from hazardous chemicals or lasers. No, they wear them to protect the chips from us. We are the walking contamination hazards. In fact, to truly eliminate human error, these environments rely heavily on keeping people from touching the product entirely. Automated robotic arms zip around, transporting the wafers and moving materials with absolutely flawless precision. Meanwhile, you've got artificial intelligence constantly monitoring the production data in real time, catching subtle little variations way before they can turn into massive, costly defects. Now, as you might guess, achieving this level of immaculate cleanliness and perfect automation does not come cheap. Tens of billions of dollars. That is the immense, mind-boggling capital cost required to build just one of these advanced fabrication plants. The construction alone takes years. Installing the equipment requires immense global coordination, and every single machine has to operate perfectly before they can even start commercial production. There's a reason why only a very, very small handful of companies globally have the capital and the supply chains to actually pull this off.
And once they are finally operational, these massive facilities have an absolute insatiable appetite for resources. First off, ultra-pure water. The manufacturing process requires massive water consumption, though thankfully, they're increasingly using incredibly strict recycling systems to offset that. Second, uninterrupted power. A perfectly stable electrical supply is absolutely non-negotiable. The local utility companies have to work hand in hand with these manufacturers because even a brief flicker in the power supply can ruin millions of dollars worth of highly sensitive chips in the blink of an eye.
Let's move to Section 4, Powering Our Digital Future, the strategic race for silicon.
All of this incredible effort, money, and precision is driving a massive global shift right now. The explosive rise of AI has turned chip manufacturing into a fiercely competitive race for tech companies and governments all over the world. It is no longer just about making consumer electronics. It's about securing the very foundation of the modern digital economy. But here's the catch. Despite all the fierce competition, no single country can do this entirely alone. Just look at the breakdown. You have precision chemicals and gases coming from one specialized sector, advanced optical systems for the lithography machines from another, industrial coordination software, the foundational silicon wafers themselves. It takes thousands of suppliers. It relies on an intricate, continent-spanning global village. Pushing the boundaries in the space absolutely depends on collaboration across borders.
Yet for all the AI, all the flawless robotics, the multi-billion-dollar machines, and these sprawling global supply chains, the single most valuable ingredient remains human knowledge. It's the scientists developing completely new materials, the engineers designing that insanely complex manufacturing equipment, the technicians who keep the systems running day and night, and the researchers constantly pushing the absolute limits of physics. Decades of accumulated human expertise is the true engine driving the innovation inside these pristine rooms. Which brings us to a really powerful thought to sum all this up. The world's most advanced factory isn't just building computer chips. It's building the future, 1 nanometer at a time. I think that perfectly drives home the profound importance of what's happening behind those extremely ordinary-looking gray walls we talked about at the very beginning of this explainer. Without light, silicon, chemistry, robotics, and physics all converging perfectly in those rooms, our entire digital age would just vanish. So, I want to leave you with one final question to think about. We constantly celebrate the flashy devices that change the world, right? The newest smartphone, the sleekest electric car, the smartest new AI model. But shouldn't we celebrate the places where they're actually born? Humanity's greatest hidden engineering achievement happens every single day in these factories. Thank you so much for joining me on this explainer. If you found this journey into the world's most advanced factory as fascinating as I did, make sure you subscribe for more deep dives into the incredible technologies shaping our world. See you next time.